There we go. Cool. Okay. So on to line integrals. Let me remind you of what we did last time first, briefly. So recall that the last lecture was about path integrals. The words path integrals, line integrals, sometimes they might get mixed up. They're pretty similar things, but path integrals were as follows. If we wanted to integrate some function over some path, there was a formula for it that we learned. It was from the time the path starts to the time the path ends. T times the differential path length element dt. So this was for when, like I said, you had some path C and you wanted to integrate a scalar function over the path. So today we're going to try to generalize this concept of integrating over paths to vector valued functions, right? In other words, instead of the function, the integrand being a scalar, today we're going to let it be a vector and try to make sense of that. And the whole concept is motivated by physics, actually. So the motivation comes from the concept of work in physics. So you might have learned what work is. A very simple definition of work is force times distance. Okay, so if you apply a constant force to some object and you move it at displacement d, well, then the work done is just F times d, or it taking dimension, 2 or 3 dimensions into account. Really, it should be F dotted with d, because by definition, work only acts in the direction of motion. So work is like what you do. Let's say if you, I don't know, if you push a car up a hill, you had to work against gravity. You had to exert force on that car to get it to move. On the other hand, if let's say you walk from one side of your room to the other side of your room. Now, for the duration of that walk, gravity was pulling you straight down, but you were walking perpendicular to the force of gravity. So for that little example, gravity did not do any work. So the whole idea of work being the component of force that's in the direction of motion is how we come up with this idea. Now, the F dotted with D formula is, like I said, is the formula for a constant force applied in a very simple linear displacement. Oops, like maybe this was the displacement and this was the force. What if the force varies with your position? So, for example, if an asteroid flies by the Earth, well, the force of gravity depends on how close you are to the planet. The force gets stronger when you get closer to the planet. So, more generally, we should be considering forces that depend on position. So, we'll consider forces that vary with position. Remember that boldface R here will usually indicate position. Okay, so if you have some path C and you break it up into little incremental displacements as such, then you can apply the force definition on each one of those little incremental displacements. Okay, because if you you have a smooth force field, then on each one of those incremental displacements, you can use the familiar definition of work. So on each one of those incremental displacements, let's call them delta Ci. You do a little bit of work as you move the object over that displacement. The little bit of work that you do will be this expression right here. Now, you see all these formulas on the screen right here. Don't worry about them. This is all just to give you an idea of roughly where the formula that I'm going to introduce in a minute comes from. But I don't want to spend too much time on this stuff right here. So don't get caught up trying to like understand what it all means. I just want to impress upon you that if you add up the work done on a bunch of little incremental displacements, you're going to get a sum of, well, incremental works in the limit that you let the number of displacements go to infinity in the so-called continuum limit. You get this formula right here. So all that was to justify the line integral formula that I will now introduce. Like I said, you don't need to worry too much about this. I put it in the notes in case you want to like spend some time looking at it yourself. But I'm just gonna go on now to the definition of the line integral. So we define the line integral of some vector field f, which is a function depending on the position in space, and it acts along some path C. The definition is that the line integral of f over the path C is equal to this expression right here. So we evaluate the force field at points on the curve, and then we take the dot product with the velocity. So it's like you've got some path C, you've got some force field which exists at each point in space, and sometimes it's pointing one way and sometimes it's pointing another way. And as the particle moves along this path, you keep adding up the component of force that's in the direction of motion. And well, that integral sum is this expression right here. So let's just do an example, and this will probably make a bit more sense. So for my first example, let's consider the path whose components are 1, t, and t squared, as t goes from 0 to 1. In fact, let me draw this path first before I do anything else. So let's see, at t equals 0, it's right there on the x-axis at 1, 0, 0. And then it goes up to the point 1, 1, 1. It's about right there, maybe. Okay, so there's the path C. I suppose I should figure out its velocity. So C prime of t will be 0, 1, 2t. That's my velocity at points on the trajectory. Right, so that would be an example of a velocity vector. And according to the line integral formula, and now let's let our force field just be the f of r equals r. Right, so this is an example of a force field or a vector field, a pretty simple one, where the value of the vector at a point is the same as the position vector to that point. So it kind of looks like, let's see if I can draw what some examples of f might be like. There's some f vectors. At each point, they're just pointing in the position vector of that point. So let's employ the line integral formula and do this computation. According to the line integral formula, this will be the integral from 0 to 1 of f of c of t. Let's see. That's just going to be c of t, actually, which is 1t squared, dotted with c prime. That's 0, 1, 2t dt. So taking the dot product, we get, let's see, 0 plus t plus 2t cubed performing the integration. We get 1/2 t squared, and then let's see, that'll be 1/2 t to the 4th. This is 1/2 plus 1/2, which is 1. Any questions on this one? Okay, if there's no questions, then let me say a bit more about the line integral formula. It's possible to express a line integral as something that looks like a path integral. Let me show you what I mean. So this is our new line integral expression. In case it wasn't clear, by the way, this term is notation to indicate that we are asking for a line integral. This term was how you compute it, right? That's how we defined what the line integral was. So let me manipulate this integrand a little bit by multiplying and dividing by the same quantity. I'm going to multiply and divide by the length of c prime, by the velocity. When I do that, I get this expression here. And in fact, let me add some parentheses to it. So the term inside the brackets, is it a vector or a scalar? It's a scalar, yeah, because there's a dot product right there. Okay, so this is the integral of a scalar times a differential path length element. This is a path integral, the integral of a scalar over some path. And moreover, that scalar is the component of, well, let's look at what f is being dotted with. This right here is the unit vector. in the direction of C prime. Basically in the direction of motion, okay? So this scalar right here is the component of F that's in the direction of motion. So this is what I was trying to say at the beginning of the lecture when I was talking about how work just adds up the components of force that are in the direction of motion. So we're just picking off the component that's in the direction of motion. Let's see, someone have a question? How would our equation change if F was not R? Which equation? You mean in example 1? Oh, well, it would depend on what F was. So if you pick some other function, I would use some other function here instead of just F of C being C. So yeah, I don't know if F of R, for example, if F of R was 2R, then I'd put a 2 right there. If F of R was equal, you know, to YXZ, then I would switch the Y and X components. Yeah, sure. Come on, one note. Okay. Let's see. So like I just said, the interpretation of all this is that line integrals are path integrals of the component of F in the direction of motion. Okay, now, if you read this section in the book, it's actually a pretty long section, and a lot of it is just notation and conventions. So I'm going to have to do some of that today. So let me talk about differential notation. It's kind of weird. We don't use it all that much, but we do use it some of the time. So I do have to mention it. Although it's not going to get fully explained in this class. But here's what it is. And you might have seen some of it before. Let's suppose that our vector field F has components F1, F2, and F3. And let's suppose that our path C has components X of t, Y of t, and Z of t. Well, then it's possible to write the velocity vector as dx dt, dy dt, dz dt. So if I dot the velocity vector with the vector field F, well, that's the dot product of those of this vector and this one. I get F1 dx dt, F2 dy dt, and F3 dz. I can kind of factor out the dt, or perhaps I should say cancel the dt if I put a dt on the end. Right? So if I slap a dt, a differential dt on the end of that, it's kind of like it cancels the three denominators, kind of, if we're using differential notation. So that's how we get an expression like this. This is called a differential form. Okay, it's important in differential geometry, which this class is kind of like a preview of. So you'll occasionally see it written in this class, and you can use it to rewrite a line integral. So using differential notation, a line integral might be written like this. You'll see that occasionally in this class. Now you know what it means. So like, if I wanted to rewrite the line integral from example 1 using this notation, in example 1, f of r was r, which is x, y, z. So in differential notation, I would get x dx, y dy, and z dz. So that's what that means. Okay. So yeah, I had to mention that. There's a couple notations I'm going to have to mention today. Next, I'm going to ask a question about line and path intervals. So here's the question. Should a line integral change depending on how fast you traverse it? Okay, remember, like a line integral is like the work done by a force acting on a moving particle, moving object. If the object's moving faster, but the force is still the same, did it do more work or less work? And similarly, relatedly, what if we ask the same question for a path integral? So what I just said was this question right here. Does the speed at which we traverse a path affect the line or path integral that we're trying to calculate? And the answer might surprise you, okay? Like probably you would think, well, if I go faster, that requires more energy, so more work, right? Not so fast. So I'm now going to attempt to answer this question, but to do so, I first need to talk about reparametrizations. Okay, so bear with me here. This is going to look probably kind of confusing. It's not that confusing once you see some examples. So reparametrizations. Suppose that we have two intervals, I and I1, okay? I is the interval AB, I1 is the interval A1, B1. And we have some function which goes from the first interval to the second interval. So maybe I should draw them. How about, let's say, here's I, which goes from A to B. And let's say here's I1, and we have some function H, okay, which goes from I to I1, and H is one-to-one, onto, and continuously differential. Suppose that we have some path C, which is defined on I1. So C takes I1 into, let's say, the plane, right? Maybe you get some path C like that. Well, you can reparametrize the path C to instead be defined on the first interval I. And you can do that by, come on, one. You can do that by composing it with this function H. So if we define a new function P as the composition of C with H, that gives us a new path. This new path goes straight from I to the plane, right? Like you plug in T into H, and then you plug H into C. That gives you this new path, and we call it a reparametrization of the first path. So here, let me just show you an example. How about the path? Let's let C of t be the path cos t sine t for t in 0 to 2 pi. This is a path we've seen many examples of. It's the unit circle. Right? It starts out when time is 0 at 1, 0, 0, then starts moving around in the counterclockwise direction. It hits the y-axis at time pi over 2, goes all the way around. It makes it back home to where it started in 2 pi units of time. Okay, so it took 2 pi seconds, hours, nanoseconds, whatever our units of time are, it took 2 pi of them to go all the way around the circle. Here, so like maybe this chipmunk is moving around the circle every 2 pi seconds. Okay, now we can reparametrize this path. I propose a that reparametrized path P of t is cos t over 2 sine t over 2. So let's try plugging in some time values and seeing what the new path looks like. So let's see, if I plot points for P of t, it still starts at 0. And as you plug in time values, let's see, it hits the y-axis at time pi. If you plug in pi, you get, pi over 2, sine pi over 2. And it hits this point at time 2 pi, and it continues to go all the way around the circle and makes it all the way back home in 4 pi seconds. So this path, it's like the first one, but moves at half speed. Okay, so the second path is like the first one, except traversed at half speed. That's an example of a reparametrization. There's a million different reparametrizations. That's one of them. In this example, by the way, so the function h of t apparently was t over 2. Right? Like if in comparison with the definition of reparametrization, that function h, in this example, it was t over 2. Okay. Any questions on this so far?
As far as other examples of reparametrization, would another example be like it moves backwards along the path, or does reparametrization only have to do with the speed at which it goes along the path?
Oh, yeah. So you're anticipating the next issue. So whether it moves backward or forward actually is the fundamental distinction between the two different types of reparametrizations. So if that's exactly what I'm about to talk about. If H is a one-to-one continuous map between intervals, well, then it's either increasing or decreasing. That's the only two. You can't like increase and then decrease while still being one-to-one. So it's either all increasing or all decreasing. And these two possibilities separate the two possible types of reparametrizations. So like I said, if it's increasing, which corresponds to the derivative being positive, that's one possibility. And if that's the case, then we say that the reparametrization is orientation preserving. Okay. On the other hand, if it's decreasing, which is to say the derivative is negative, well, in that case, then we say that the reparametrization is orientation reversing. In example 2 right here, let's see, so H prime was 1/2, which is positive. So this one was orientation preserving. Even though it went slower, it was still going in the same direction. So let's look at one that would be orientation reversing.
Can I ask a question about the example we were just doing?
Mhm.
So like we said, H is supposed to be a function from L to L1. And
I to I1.
I to L. So I in this case would be 0 to 2 pi, and I1 would be 0 to 4 pi.
Oh, oops, sorry. Actually, there should be a 1 right there. It looks like the way I had it set up, I1 was 0 to 2 pi. This
Okay.
one was
Okay.
I1.
Okay. Yeah. That makes
It's not a big deal, but yeah, thanks for pointing that out. Okay, so let's try one that's orientation reversing. How about again, if let's use the same C of t, which was cos t sine t. And t is in 0 to 2 pi. So we already know that this just goes around the circle in 2 pi. So that's C. Then a reparametrization that corresponds to moving in the opposite direction. Like I said, there's many. Oh wait, Rob asked why it's onto.
That was kind of what you just addressed, because I had I and I1 mixed up. And...
Oh, okay. So there's many possible reparametrizations, but how about this one? So how about if we let P of t be cos of 2 pi minus t, sine of 2 pi minus t, then let's plot P of t. Starts at 0. At pi over 2, it's right here, right? Like P of pi over 2 is cos of 3 pi over 2, sine of 3 pi over 2. So in this case, P moves in the opposite direction around the circle. And this is an example of an orientation reversing reparametrization, right? Like h of t in this example would be 2 pi minus t. Notice that h prime is negative. So this one is orientation reversing. And in general, in fact, here's a notation which we will occasionally use. If we're given some path C, then denote by C sub op the opposite path, which starts at the endpoint and ends at the start point. And you could actually write a formula for it given by this formula right here. You don't have to worry too much about the formula, but basically the idea is if that's what C looks like, then let's see. Then that's what C up will look like. Okay, so now I'm ready to answer those questions that I posed before I started talking about reparametrizations, which was how do they affect line integrals and path integrals? So I've got 3 theorems that relates to all this. The first one is about line integrals. So theorem 1, if P is a reparametrization of some path C, then there's only 2 possibilities for how it affects the line integral. If it's orientation preserving, then the line integrals are unaffected. So as long as you move in the same direction, you're going to get the same number for the line integral. Kind of amazing, right? So the amount of energy expended doesn't depend on how fast you traverse the path. On the other hand, if it's orientation reversing, then the line integral is affected. It picks up a minus sign. But other than that, it's the same. So this theorem has multiple consequences. The first one is that traversing a path at a different speed doesn't change the line integral, except if you move in the opposite direction, in which case you get a minus sign. And it kind of makes sense, like if this is the path C and this is your force field F. If you move in the opposite direction, then all your dot products are going to be the negative of what they were with the first orientation. So that kind of explains where the minus sign comes from. Secondly, I now apply the same question to the issue of path integrals. So what if you're integrating a scalar function? In this case, the path integrals are totally unchanged, even if you go in the opposite direction. Right? So the path integral of a scalar function is unchanged by a reparametrization, even if it changes the orientation. So it doesn't matter how fast you traverse the path, you're going to get the same number regardless for the path integral. I could prove all of these, by the way. I don't have time to, but you can see some of the proofs in the book, or I can show them to you in office hours. They all basically come down to the chain rule and the change of variables formula. Finally, we've got a related theorem, which is of a somewhat different character. So this is an important theorem, which you probably heard about in physics. Suppose that we have some vector field that's a gradient, right? This was a special type of vector field that was equal to the gradient of some scalar function. If you have a vector field that's a gradient, and you've got some path, and you're integrating this vector field over the path, then what you get as a result is just the scalar function evaluated at the 2 endpoints of the path. So f at one endpoint minus f at the other endpoint. So this is kind of amazing. It says it doesn't matter how you got from one endpoint to the other, right? Like, let's say this is some path C, and you're in some scalar field. Well, as long as the scalar field is a gradient, it doesn't matter how you got from this point to this one. You'll get the same answer even if you go on this very long, windy, circuitous route. It only depends on the two endpoints of the path. Now, I could prove this. Oops. And it's not hard to prove. I think I don't have time to do it now. So I'll just mention really briefly the idea of the proof. It's just the fundamental theorem of calculus and the chain rule. So I wrote down the idea here. I don't have time to talk about it right now, but you can look at it on your own later or talk to me about it in office hours. Let me just reiterate the point of this theorem once again, because you might have heard it, especially in the context of physics. There's another name for vector fields that are gradients. They're also called conservative vector fields. So conservative vector fields are the same as gradients. Same thing, two words that mean the same thing. You'll hear either word to mean vector fields that are gradients. They're very important. A lot of the fundamental force fields in physics are gradients. Gravity, that's a gradient. Even the local flat approximation to gravity, that's a gradient. Electrostatic energy, that's a gradient. The spring force, that's a gradient. So yeah, all sorts of forces, common forces are gradients. In this terminology, theorem 3 can be summed up in the expression, the line interval of a conservative vector field is path independent. That's what I'm saying when I drew this, because it doesn't matter how you got from one point to the other. You can go to the other side of the universe, and as long as you end at the same point, the integral is going to be the same. The word conservative comes from the conservation of energy, because that's what we're calculating with these integrals is energy. So the path independence means that the energy is conserved. An example of something that would not be path independent would be frictional forces. Those do depend. When you've got energy loss due to friction, those come from forces that are not conservative. Okay, so dang, I don't think I'm gonna have time to do this example. Maybe I can. Okay, by the way, there's a few types of curves which I do not have time to talk about. I'll just show you very quickly that the book tells you that a simple curve is something like this, in contrast with a not simple curve, which has a point of intersection. Okay, so simple curves can't intersect. Oriented curves have a direction. An oriented curve is just a curve that someone also said there's a direction on this curve. We sometimes indicate them with little arrows. And finally, a closed curve is one that forms a loop. It ends where it started. Okay, let me try to make it something like that. There we go. Okay, so you can read about these types of curves in the book. The book goes on for much longer about them than I have time to do here. The last thing I wanted to do was this example with Black's Beach to sort of illustrate all these concepts. So I'm probably going to go a couple minutes over, but I think it's worth it to sort of cement these concepts. So here's the problem. Suppose that we climb from Black's Beach, which let's position at the origin, up to Glider Port, which I'll position at the point 001. So here's the beach. down here, and glider port is up here on the top of this cliff, right? So there you got people in the gliders up there, and you want to you're down here at the beach, and you need to make it up to the top of the cliff. Now, I'm offering you two different paths to get from the bottom to the top of the cliff. You can move in a straight line path, which I labeled as D of t. So that's the first path. Or you can go in this like curvy path, which I called C of t, and it looks something like that. So as you go up glider port, I don't know how many of you have climbed the stairs at glider port from the beach. It's kind of a workout because you have to work against gravity to go from the beach up to the top of the cliff. So that whole time you're working against the force of gravity, which exerts a, let's say, uniform force in the -1 direction. So gravity is always pointing straight down, let's just say with magnitude 1 in the -z direction. Let's then calculate some of these line integrals. So let's see. Okay, here, I'll do the first one and the second, and then I'm going to ask you to do 3 and 4. So the first one, let's find the force, or sorry, the work done by gravity if we go up the curvy path. That will be F, okay, F dot ds on the curvy path is 0, 0, -1, dotted with, let's see, C prime. So that'll be 0, 2t minus 1, 5t to the 4th dt. This is the integral from 0 to 1 of -5t to the 4th, which is t to the 5th from 0 to 1, which is 1. Okay, so 1 joule of energy was done by gravity in this trip. What if instead you just went straight up the sheer side of the cliff via the path that I called D? So this starts and ends at the same location, but travels a different way. In this case, let's see what we get. This will be the integral from 0 to 1. 0, 0, -1, dotted with, let's see, in this case, what was the formula? Come on. 0, 0, t. So d prime of t is 0, 0, 1. So I'll get a 0, 0, 1. This just ends up being negative. Oh, wait, I lost a minus sign here. Sorry about that. There's a minus sign right there. Minus sign should be there, minus sign should be there. So I get the same answer via this second path. Okay. Now I want to test you all on this. Oh, I see some. Yeah, Roland. Roland and Rob spoke up. Good. Yes. Yeah. You're right. It should have been negative. Okay. How about you private message me the answer to 3? What's the work done if we go down the curvy path in the opposite direction? Oh, cool. Good. Yeah. All right. Nice. Yeah, you guys are getting it. So if I went down in the opposite direction, that means I'll just pick up a negative sign. So that'll be the negative of the previous answer, which is +1. Okay. How about private message me the integral of the path length, or the integral of the differential curve length element. Look at the path. Oh, cool. Okay, yeah, this is just the length of that path. Doesn't even matter that we went in the opposite direction. The length is still the same. Good. Yeah, this is the length of that path, which is 1. Finally, is F conservative? Like, it seems like it's conservative because we got the same answer for paths 1 and 2. That just means those 2 happen to get the same number. That doesn't prove that it's conservative, though. So the results thus far suggest it is. Is there a way that we could know? In fact, there is. Now, more on this later. For now, let me just prove it to you. So the answer is yes. Because if f of x, y, z is negative z, then f, capital F, is the gradient of little. So that proves that it's a gradient. And we learned today that the integral of a gradient field is path independent. Cool. Okay, that's it, folks. Sorry for going over there. There was a lot I had to try to fit in a 7.2 lecture. So have a nice weekend. Yeah, again, sorry for holding on to you guys late. I know it's the weekend. You probably want to get going, and I'll see y'all next week.
Thank you.
You're welcome.
Professor, what exactly is the point of reparametrization? Like, why would I want to make the unit circle equal to cosine t over 2, sine t over 2 with t over 0 to 4 pi instead of just the usual way?
Well, a lot of times we use parametrizations to represent trajectories that have a certain position at a certain time. So, I mean, there's many different ways that you could travel the same path. if you travel it at a different speed or in a different direction. So you would use a reparametrization to represent a journey along the path at a different speed. There's also, in fact, there's one very special parametrization. So among all possible parametrizations of a given curve, there's one special one that's called parametrizing by unit speed. It's the one that corresponds to moving with speed 1 along the path. So often you want to parametrize or reparametrize by unit speed because it makes a lot of the other calculations come out quite nicely, and it allows you to define the unit normal and tangent to the trajectory, which is then necessary to define concepts such as curvature. So this is all getting into differential geometry, which is actually a pretty tough subject, but it's pretty interesting. And it's fundamental if you want to ever understand general relativity.
Is the unit time, is that supposed to be from t 0 to 1?
Yeah. Well, actually, it doesn't necessarily. No, sorry. No, not necessarily. It just means that the distance
Right,
you've
yeah.
traveled is equal to the length of time that you've been traveling.
Right, yeah, sorry, I just forgot what t meant for a second. Right, yeah. All right then, thanks.
Yeah, good question.
All right, good on.